Check it.
Okay, welcome back. Today we're going to be talking about solving equations with exponentials in them. So we spent the last couple of lessons graphing exponentials, exponential growth, exponential decay. But what about solving equations? Well, the fact is you cannot solve all exponential equations by hand unless you use something called a logarithm, which we're going to learn in the next section. However, for the time being, we're going to use some workarounds to solve some of the simpler ones. Like for instance, 3 to the x equals 27. All right? You can probably figure out just by guessing and checking that, well, 3 to the first power is 3, and 3 to the second power is 9, and 3 to the third power, that's 27. So if 3 to the third power is 27, then the x and the 3 must be the same number. So you can surmise from that that x equals 3. Okay? So that was doable because it was super easy. It was a very simple example. But what if you have something like 3 to the x equals 10? Now what do? Well, once again, you know that 3 to the first power is 3. You know that 3 to the second power is 9. And you know that 3 to the third power is 27. But where's 10 in all this? 10 would be somewhere in between 3 squared and 3 to the third power. So x would be somewhere in the middle between 2 and 3, but the question is, what is it? Now you can guess and check and try different numbers on a calculator till you come close, but that's not the way we do math. We're not going to guess and check our way into an estimate here. We want to know how to get an exact answer for x. So we can say, yeah, it's probably about 2.1 or 2 point something like that, but we don't know. And we're not going to guess and check. All right? So how do we handle these problems? If you cannot do them without guessing and checking, how do you solve them? Well, we're going to solve them with logarithms later on. But what if you have something like this? If you have a situation where you have 3 to the x equals 3 to the fifth power, the bases are the same. And something called the base property of equality says that if you have two numbers that are the same base, their powers must be equal if they're set up like this in an equation. So essentially, this means that if 3 to the something equals 3 to the something, those somethings must be the same thing. So effectively what you're doing is you're ignoring the bases here and you're getting x equals 5. And if you think about that, we could have actually come back up to this first example here. Let me back up a little bit. Isn't 27 equal to 3 to the third power? So we could have rewritten this problem as that. And see, because the bases match, you can, as the 80s rapper once said, drop the base. And now you have x equals 3, which is the same thing we got before by kind of reasoning it out. So I guess the theme here is, the theme here is that if you could find a common base for both sides of the equation, then you can drop the bases and you can take the exponents and make an equation out of them, and then you can solve for x. That's the idea here. Now you'll see that this does not work all the time. It works for the first one because 27 is 3 to the third. It works for the bottom one here because this is 3 to the fifth, but there's no power of 3 that will give you 10. So for something like this, you have two options: guess and check, which we don't do, or learn to use logarithms, which we will do pretty soon. All right, so let's get on with the easy version here, which I refer to as base matching. Okay, so we're using the base property of equality here, and the idea is, can you get the bases, the b's, to match so that you can drop the base? Okay, and then you just get x equals y. I have some notes here. The goal is to get the bases to match, and the big question is, can I drop the bases yet? So we're going to do some steps, and when it's time to drop the base, we'll drop the base, but not before that. All right, so here's a couple of examples. So we have 2 to the x equals 8 to the third. The bases do not match yet. Now, what we want to do is, and now here's the thing, like I said, not all problems are solvable, but the ones in this section and tonight's homework, they are all solvable by base matching because that's what we're learning. So there has to be, because we're in this section about base matching, there has to be a way to make these both the same number. Okay? And if you think about it, 2 is a prime number, so we really can't change it or break it down in any way, but 8 is not a prime number. So how about we do a factor tree for 8? We come over here. We say, all right, 8 is what? 4 times 2, and then 4 is 2 times 2, and this is 2. So really, 8 is just 2 to the third power. right? And that is a base of 2 right there. And this is a base of 2 right here. So that would be the same base. That would be matching the bases. So we'll redo this equation here. This 2 to the x remains 2 to the x. But this 8 now becomes a 2 to the 3rd power. So this 8 is now that. Okay? And now leave that alone. That's your 8. Don't get confused with this 3rd power here. There's still a 3rd power out here. So this 3 is this 3 here. And this 2 to the 3rd, that's this 8 right here. So now we have this. Can we drop the bases yet? Not yet. The reason why we can't drop them yet is because we have some multiplying to do here. This is a power of a power. 2 to the 3rd to the 3rd. So we have to multiply the powers. When you have a power of a power, you multiply the powers. So we have to simplify this first. So this becomes 2 to the x. Well, not becomes. This is still 2 to the x. This is still equal. But now this is 2 to the 9th. Are the bases the same? Yes. Are the powers fully simplified? Yes. Can we drop the base now? Yes. Drop the base. And now we get x equals 9, and we're done. Once again, you might be thinking, well, what if this was 7 to the 3rd? Nope. Wouldn't work. We'd need logarithms. But for these problems, we will be able to use base matching. Okay, let's try another one. Now, take a wild guess what the common base is going to be on this one. You have a 9 and a 3. Now, the 3 is prime, so no need to make a factor tree for 3. But 9, well, 9 is 3 squared. I don't think we have to literally write the factor tree out. So 9 is 3 squared. So there you go. You have your common base. It's going to be 3. So this 9 becomes a 3 squared. And then you have your 2x minus 1 there. And this one here is already a base of 3, so there's no reason to do anything with that. And there you go. Can I drop the bases yet? Not yet, because I have to do the multiplying here. So we have to multiply 2 times 2x minus 1. So it's 2 terms. We'll distribute. And let's see what we get. We get 3 to the power of 4x minus 2. And this is 3 to the 6x still. Do the bases match? Yes. Are the powers fully simplified? Yes. Drop the base. So we get 4x minus 2 equals 6x. And now you're in Algebra 1 land. You just have to solve the equation, get x by itself. Now, in case you're a little rusty on Algebra 1 stuff, when you have x's on both sides of the equation, you can't solve for x. You can't get x by itself if there are more than one of them. And you can't combine like terms because they're not on the same side of the equation. So you decide to get rid of one of them. And it's usually the smart thing to do to get rid of the smaller one, so the one that remains is a positive number rather than a negative. It helps a lot with inequalities as well, so you don't have to worry about D-band. So we have a 4x, we have a 6x, which is smaller. 4x is smaller, so let's get rid of that. How do you get rid of a positive 4x? You subtract it, put a minus 4x underneath, and of course you have to do that to both sides. That's gone, and 6x minus 4x is 2x, and now we need to get the x by itself, so we'll divide by 2, and we get x equals, this is going to be a negative 1 right here, but we'll flip it around because your variable should be on the left. This is negative 1, and we're done. Now if you like, you can plug in negative 1 for your powers and see if they match here. So as a check, now these aren't as required as they are for the radicals that we did last chapter, but you know, checking your work is never a bad thing. So this is 9 times 2 to the negative 1 minus 1 has to equal 3 to the 6 times negative 1. This is going to be 2 times, this is going to be negative 3 right here, and this is going to be 3 to the negative 6. And the question is, are these the same? Well, this is 3 squared, right? We just learned how to do that a minute ago. And when you multiply these, you get 3 to the negative 6 equals 3 to the negative 6. So the check is not required here. I'm just showing you that the answer is correct. So we know this is right. Okay, all right. What about inequalities? All right, well, inequalities are just like solving equations, except you have less than and greater than. You have to be on the lookout for D-band, divide by a negative, right? Always be looking for that when you're doing inequalities. If you divide both sides by a negative, flip the inequality. And I need to see your answer on a number line, regardless of whether the book asks you to or not. So let's go ahead and try an inequality using the exact same idea here. So we need to find a common base for 16 and 8. Now, you might think, 4 might work, but the truth is, yes, 4 squared would give you 16, but there's no power of 4 that gives you 8, so don't fall for that. It wouldn't work for 4. But yeah, actually 16, if you do a factor tree here for 16 and 8, you'll find they do have a common base. So 16 and 8, This is 4 times 4, and this is 4 times 2, and this is 2 times 2, and this is 2 times 2, and this is 2 times 2, and this is 2. So 16 is 2 to the 4th power, and 8 is 2 to the 3rd power. They're both multiples of 2. Not multiples of 2. They both are powers of 2. So 4 doesn't work because you can't take a power of 4 and get 8 unless that power is a fraction. But 2 definitely works. So this is going to be 2 to the 4th power, and this is going to be 2 to the 3rd power. And we'll put our parentheses just like we did in the last couple problems here. And the 2x minus 3 is still there. The less than is still here. And this one doesn't have anything out here, so we're done here. Okay, so here we are. Can we drop the base yet? No, because we still have to distribute that 4 right there, right? So what do we get? Well, this becomes 2 to the power of 8x minus 12 is less than 2 to the 3rd. Are the bases the same? Yes. Are the powers simplified? Yes. Can we drop the base? Drop the base. And now we have an inequality algebra 1 style. Just solve for x. Okay? And don't forget to put your answer on a number line when you're done. So let's see. We'll add 12 to both sides. We get 8x is less than 15. Divide both sides by 8. And we get x is less than 15 over 8. And that's our inequality answer. But I also want to see it on a number line here. So 15 over 8. This is going to be an open circle, shading to the less than side, which is the left. And what this symbolizes is that you have an infinite number of answers, not just 15 over 8, but everything less than that. So this is around 1.8 or 1.9 right here. It's, 0 will be somewhere over here, let's say, and then it just would keep going down to negative infinity. All of those answers would work in here and give you a true result. Okay, let's try another one here. We have another inequality, and this one looks a little strange. I mean, you got a fraction here. Let's see what we can do with this. Now, the good news is one of the bases is prime, right here, 3. So you know that has to be the common base. So the question is, how do you get this to become a power of 3 right here? Because you can't do anything with this. That's prime, right? Factor tree will not go anywhere. So if one of them is prime, that's got to be the common base. So the question is, how do you get this thing to be the same as this? So what we'll do is take a look at 243 here. It's 243, but it's got a 1 underneath it. Or it's underneath a 1, rather. So really, it's 243 to the negative 1. That's what that is. So the question is, what is 243, though? We'll worry about the negative 1 flip thing later. Let's just deal with 243. So let's just take the 243 and make a factor tree out of it. And if you're not sure where to go with that, try dividing it by 2. Well, you can't because it's not even. Try dividing it by 3 and with a calculator, and you'll realize, hey, this is 81 times 3, okay? And 81 is 9 times 9. And each one of these 9s is a 3 times 3. And here you have a 3 times 3 times 3 times 3 times. This is 3 to the 5th power. Hey, it is a power of 3. What do you know? But it's not a 243. It's a 1 over 243. So it's a 1 over 3 to the 5th power, which means that this is actually 3 to the negative 5th power. Okay, remember, negative power means you're flipping it. So this right here, this whole thing is actually 3 to the negative 5th power. So I can rewrite my inequality here and replace this with a 3 to the negative 5th power, like that, okay? And just to convince you, this would normally become 1 over 3 to the positive 5th, and that would become 1 over 243 when you expanded it. So we know it worked. Now, are the bases the same? Yes. Are the powers simplified? Yes. Can we drop the base? Drop the base. And now we have this simple inequality that we can solve algebra 1 style. Okay, we can add 1 to both sides, add 1 here, that goes away, add 1 here, this becomes negative 4. We're going to divide both sides by positive 2. Dividing by a positive, not D-band, that's D-BAP, and D-BAP is not a thing, right? So you're not going to flip any inequalities here, and this becomes negative 2. So there's your algebraic answer. Let's do it graphically as well. Okay, this is going to be negative 2, and it's going to be all the numbers that are equal to and greater than, so close circle, shade to the right. A little bit of number line practice with all the inequalities here. There you go. And those are your answers right there. All right, this next section is about writing an exponential function given 2 points. So yeah, the idea is this. We're going to give you 2 points. Let's say this one and this one. And because we read our graphs from left to right, we can tell that this function is going up, because from here you're going from a low point to a high point. So this is exponential growth. And we know it's got to be this shape because we've learned the shape. when we were doing our graphing. So if I give you this x and y, call it x1, y1, and this x and y, x2, y2, you should be able to give me y equals ab to the x, the function that would go through these 2 points exponentially. All right, so that's the idea here. So I have got some notes here on the process, but let me just show you how to do it. So here's the example. Write an exponential function that goes through the points 0, 7 and 3, 105. And then when you're done, use that function to find me the value of g of 15. So what we want is a function that's an exponential function. So all exponential functions are in the form b to the x, and if there's a stretch, it would be a. All right, and so ab to the x, and we're not going to worry about shifting. There's no h and k here. So this is what we're looking for. Y equals b to the x. This is the general formula. Y equals ab to the x. But because I told you it's going to be called g of x, you need to use that name instead of y. So g of x, like that. And now the question is, what's the function? Well, the function would be complete if you just knew what a and b were, right? Like for instance, if you knew a was 3, that would be a 3. And if you knew b was like 7, then that would be a 7. And there you go. You would have a function, right? The question is, what is a and what is b, and how do you find them? So here's what we're going to do. We're going to use the 2 points that we were given to find a and then to find b. So we're going to do this process twice. First, we're going to do a process to find a, and then we're going to repeat the process to find b. So I'm going to write this twice here because we're going to need it twice. The first thing we're going to do is look at the point that has a 0 for an x. Anytime your x is 0, this has to be a y-intercept. So we're going to take the y-intercept. And you notice in that sketch that I made a few minutes ago that I put it on the y-axis. Yeah, one of them is going to be a y-intercept. That's part of the deal here. We know that at this point, x is 0 because it's a y-intercept and y is 7. So we can replace this x and this y, because this is supposed to be a y here, with this and this, right? So here's what we get. This is the y, which is 7, and this is the x, which is 0. And we hopefully know that anything to the 0 power is a 1. So this is just a times 1. So for all intents and purposes, this is gone. So we get 7 equals a, so a is 7. Boom. There it is. And now we know that that's going to be a 7. Okay, we're halfway home. Now the question is, what is b? How do we find b? So we start the process again. But this time, since we know a is 7, we'll plug in the 7 and we'll start over. This time we're going to use the second point they gave us. Here the x is 3, so we'll put in a 3 right here. And the y is 105, we'll put a 105 there. So what we have here is 105 equals 7b to the third. And you notice that the only thing that is still unknown is the b, and we can get the b by itself and we can solve. So this is where you're going to reach for a calculator, because these tend to get a little big with the numbers. On the homework, you're going to see some rather large numbers. That's okay. So how do we get the b by itself here? Well, we're going to divide by 7. That'll get rid of the 7. And we get 105 over 7. I'm going to flip this around so that the b is on the left. So b to the third equals 105 over 7. Now what is 105 over 7? 105 divided by 7 is 15. And now how do I get rid of this third power here? Well, we have two options. We can either take this to the power of the multiplicative inverse, the way I taught you a little while ago, or equivalently, we could just take the third root of both sides, right? The third root would cancel out the third power, which is the same thing because a third root is a 1/3 power. They're one and the same. Either way. So you get a b here. And now this is whatever the third root of 15 is. We could leave it as a third of 15 in the equation, but the problems in the homework are all decimal based, so I'm going to go ahead and just use the calculator here. You can either go 15 to the power of, always put your fractions in parentheses in the calculator like this, to the power of 1/3, and you'll get this right here, which is, and we'll take it to the third decimal place here, 2.466. Or I could have gone to the math menu, chose the third root button, the cube root button right there, put in 15, and gotten the exact same answer. So either way. Now that I know a and I know b, I can write my equation. So it's g of x equals a, which we know is 7, times b, which is 2.466 to the power of x. Now here's the thing. How do you separate the 7 from the 2.466? We put parentheses around that. And there's your equation. That function, if I were to graph it on Desmos or in this graphing calculator here, would be a function that went through the point 0, 0, and it would go through the point 3, 105. All right. Now the next thing we have to do is find the value of g of 15. So basically what we want to do is plug a 15 here, right? So g of 15 equals this whole thing here to the 15th power. And let's see, I guess we can just come over here and do it. That'll be 7 times 2.466. Actually, this is rounded off. If I really wanted it to be a little better, I could leave it as a third root of 15, but to the power of 15. Now, the calculator knows to do the power before it multiplies by 7. It knows it's PEMDAS. And what we get is g of 15 equals 5308772.613. So 5,308,772.613. Like I told you, these numbers get kind of big, so a calculator will be helpful here. Okay, let's try another one. This one's in the form of a word problem. Yes, I know you all love word problems. Okay, so let's just drag this down here for the moment. Kristen starts an experiment with 7,500 bacteria cells. After 4 hours, there are 23,000 cells. Write an exponential function that could use to be a model of the number of bacteria after X hours. Okay, and then the second one is how many bacteria can be expected after 12 hours. So let's just focus on A. We want to write the function. So like I told you in the previous example, what you need here is 2 points. If you have 2 points, you can find your y equals ab to the x function, right? So what are our 2 points? Well, Kristen starts the experiment with 7,500 cells of bacteria, right? X is the number of hours. So if you think about it, you do have 2 points here, because when she starts the experiment, you're at 0 hours, right? And you have 7,500 cells. And when you're 4 hours later, your X is 4, because X is hours again. And you now have 23,000 cells, bacteria cells, right? So you do have 2 points, and there they are. And you're going to do the exact same process we did before, which is take the y equals ab to the x. Last time it was called g of x. This time we're just going to leave it as y. And you're going to plug in this x and this y, and you're going to find your a that way. So x is going to be 0. Once again, you have to start with the y-intercept, so this is always going to be 0. And this is always going to be, well, whatever the y-intercept y coordinate is here. So you have that. And so now we have 7,500 equals a b to the 0. And once again, anything to the 0 except 0, anything to the 0, any non-zero number to the 0 power is going to be a 1. So that's essentially a 1 right there. And a times 1 is just a. So there you go. There's your a. A is 7,500. Just like before, we get the a pretty quickly. Now we can take the equation, plug in that a, 7,500, and now use that with the second point. This is also going to be x and y. We're going to make x 4 and y 23,000 and find b this time. So this is going to be 23,000 equals 7,500 b to the 4th. And our job now is to get b by itself. So how do we get this b by itself? Well, the first thing we're going to do is get rid of the 7,500. So we'll divide both sides by 7,500. That cancels out. And right away I can see that this 0 will cancel out this 0 and this 0 will cancel out this 0. So you have 230 over 75 now. And we'll flip it around. B to the 4th equals 230 over 75. And, or you can just leave the zeros on and use the calculator with that. It doesn't matter. Either way, you're going to get the same answer. So what is 230 divided by 75? We get 3.06 repeating, right? So B is going to be that. B to the 4th is going to be that. So how do we get the B by itself? Well, we'll take the 4th root of both sides. Now, I'm not going to round this off here because that'll make the round off error even worse. So we'll just leave it the way it is on the thing here. I'm going to write to the power of, and then a way to take a 4th root, I can either use the x root button or I can take this to the power of 1/4. So I'm just going to take that shorter cut here. And what I'm getting here is b equals, and we'll take it to 3 decimal places again, 1.323. So what's our function here? It's y equals ab to the x. We said a was 7,500 and b is 1.323 to the power of x. There's the answer for part A. That's the function. And now the question was, how many bacteria cells do you have after 12 hours? Well, you just have to take this and plug in a 12 for x, right? So how many bacteria cells do you have after 12 hours? plug in the 12 right there. So what is 7,500 times 1.323? Now there's going to be a bit of a round off error here because I'm not using the full thing. 323 to the power of 12. And what I get here is y equals, and y is the number of bacteria cells, 215,664.8, but you can't have 0.8 bacteria cells. So let's just round it off to the nearest bacteria cell. Actually, not the nearest, we'll truncate it down to the that number right there. Okay, let's take a look. I think the answer is down here somewhere. Okay, well, the function is there. I guess the number of bacteria cells is not, but that you can see our function is correct right there. And plugging in a 12 is just a calculator thing. All right, that's it. We're done. See you at the next video.
Check this.